Okay, hello. I kindly greet you to my talk. I'll be speaking about wireless metering protocols. My name is Cyril Brunschwiller. I come also from Switzerland, as Sebastian does. I come from the German-speaking part. I work in a company which has a similar profile as Systream and SCRT also have. I've been studying for a Master's of Science in Information Security at the Royal Holloway University, and the output of my studies there for the master thesis is basically what I'm going to present here. So for those who have seen my talk at the Black Hat, maybe you're better off to have a coffee outside and come back for the demo afterwards. For everyone else, try to stay here. I don't have nice girls in my slides, but should be still fun. All right. I will quickly go through the smart grid and smart metering infrastructure. I will show you some picture of devices. I will then dive into the wireless meter protocol and show you the issues with the protocol, and I will show you a short demo afterwards. If we talk about the smart grid, there is a bulk generation and storage part of the grid. There's where the mass of the energy is being generated, and this will be transmitted. The operators called there are transmission service operators, TSOs. Then there are the DSOs. These are those ones who are basically carrying the energy to the cities and will be distributed then to the houses, to the masses. And there it's going to be interesting because we do have lots of consumers, and people try to get their own energy into the grid and sell it to the DSO. And they are starting to kind of also virtualizing the energy infrastructure. So they build little VPPs, virtual private plants, so where they try to arrange consumers and producers in little cells. And for that purpose, you must somehow make the grid intelligent. And therefore you need the smart metering infrastructure, so you have proper information and real-time information what currently is being consumed and generated at the far end of the grid. So if you look at the metering infrastructure, then we do have the meters in the houses, of course. In your household, there will be collectors which collect all the information from the meterings infrastructure and send it to the head end. So the head end is basically a server which is located somewhere at the distribution service operator's DMZ, and it will collect all information. The head end could also be used as an MDM. This is not a mobile device management, but it's rather a meter device management. So they do updates and push configuration out to the meters. In the middle part, in the WAN, the wide area network, we usually see TCP/IP or some let's say, power line protocol custom built. What I will be speaking of is a wireless metering protocol. It's called wireless MBus. MBus stays for meter bus, and this is basically spoken at the household part, so the neighborhood area network. If I talk about the collector, this is a picture of one. So it's got, on the head end side, it's got the TCP/IP plug. This one also fits on top rail. So you could basically use it as an interface between the dump meter and the head end. So it collects the information from the meter using various protocols, for example, ZigBee. And sends it over Ethernet to the head end. There's actually a Linux running on this system. There's a little web server as well, so I've not been digging into this device. If you want to have some fun, go for it. I'm sure there's lots of bugs. This is a piece of software which you could use to configure such systems. Here you see just an overview how many meters are actually talking to that collector and what they are talking to it. That's a meter, so The special meter is a Kamstrup electricity meter. You can basically plug any sort of communication PCB on it. So there are PCBs for ZigBee, for wireless M-Bus, for GPRS. It's plug and play. So you choose the interface you want, and they plug the correct PCB on it, and you're ready. What you could do nowadays with such meters is you could, for example, enforce payment. So people who are not timely paying their bills could be enforced to pay their energy consumption in advance, prepayment. You could also actually tell customers what the tariffs are currently, but you could also disconnect someone if he decides not to pay for energy anymore. If we look at the protocol they are talking, so the collector is basically receiving information and the meter is using the protocol to talk to the collector. It's basically used all over Europe. I have seen not many devices around the US. There should be about 15 million devices deployed now. And you could use it for various topics. It's all standardized, so it's an IEC-EN norm, it's a European norm. You will get the standards from your favorite ISO store. I have been looking at the draft standards actually, because the current standards, the active standards, they don't include any security at all. So I've been looking at the draft ones. When we look at the protocol among Europe, we mainly see them talking about 868 megahertz. There are actually also some devices which are using 169 megahertz, and with 169 megahertz you can make up to 5 miles line of sight. They use some easy line coding, and there is some sort of protocol packaging like we know from TCP/IP. So they have a frame header, they do some CRC there to detect some interferences, for example. There's the device addressing, so if the meter sends a packet, then it's gonna tell its own address, because the collector must somehow know which meter actually sent the information. There's also a part of the specification which is called the extended link layer, which does also employ some CRCs. If we look at the actual code, then there's a byte which indicates the length of the whole message. Then there will be information on manufacturer and the address of the meter. That information is being sent in plain text all over. So if you are in, which I would say, 200 to 300 meters range, you will get the information from such a wireless device. And it will basically tell you who has built the device and what exact number it has. It will also tell you, hey, I'm a water meter, I'm a gas meter, I'm an electricity meter, and what version it has. So all we need. So if there would be any issue in time with this device, you would easily find vulnerable devices. And here we have the first issue, information disclosure. That's what we see in the internet, so not to disclose server version, server type. That's what they're doing here. If we go further, there is it's called a data header. There are 3 different types of data headers. There's no header, but this, if you ever come across a packet which has no header, this is bad because there's no encryption. If you have a short header, then you can signal encryption. If there is a long header, you could also use it as some sort of, if you're familiar with TCP/IP, it's some sort of NUT. So you can signal to a collector to be kind of a gateway for some other meter. If we look at the data header, there's an access number, It's the B3 here. There's a status field and there's the configuration field. The configuration field actually signals the encryption type you're using. In this case, it's AES 128 CBC mode. And it also says 10 hex, so it means basically there's a single block AES encrypted attached. So if you have patience enough to count the numbers, it's going to be 16 bytes there. But we don't have sufficient replay prevention because the access number is basically telling the receiver which number of message it was. Okay, but if you're going to send a 255 messages, then the same access number will occur. And these meters are configured to send their values. Some do it every 10 seconds, some do it every minute. So it's very likely that these numbers will just turn over and start over. If we look at the data they are carrying, it's very structured. So there are informations of what data they are carrying and what the value form is. This example shows you basically it's telling the collector, hey, I am a data package which is a current measurement, and by the way, the value I'm sending you is in watt hours, and then the actual value, which is the 341 kilowatt hours. It's kind of difficult to find open source sniffers, so I decided to implement a little Python script. You could use this little Python script with some sort of special hardware, and I just used it to get some overview on what they are really sending around. Then I figured, okay, lots of the vendors are using encryption. I digged into the standard, and the standard clearly states at least 8 bytes of the key shall be different for each meter. But vendors don't care. They use the same keys all over and over for thousands of their meters. And the reason why they are doing is, they explained me, there's the technician. We're going to send him with a handheld device out to the houses, and he's got to reconfigure and to manage those devices. And we don't want him to hassle with all the keys. Okay, so they have the same key for all the devices. By the time one of these guys just loses his handheld device, they're lost. So we have non-keys, stupid keys, and short keys. Then I went on and was thinking about, okay, what encryption modes are available here? In the standard are basically 6 modes. Then I saw, okay, there's still this. I'm going to skip that because it makes no sense to have a close look at it. And there's also encryption at the extended link layer. They use their counter mode, and in the dedicated application layer uses CBC. So AES should be fine, right? So every meter vendor basically adverts on its website how cool AES encryption protects you from fraud if you're using their meters. It's not. Why? It's AES in CBC. They use an all-zero IV. And if you use an all-zero IV, then every message basically, every message that contains the same content will basically end in the same ciphertext. So if you say, okay, we're going to consume 10 kilowatt hours, then you apply the IV, nothing, and there's a static key, that's the issue, or the IV, however you want to turn it. And then we get the ciphertext block. And if you're not at home, you're not using any energy, right? Or not much. So it's still 10 kilowatt hours, It's still the same IV and it's still the same key, so turns out it's the same ciphertext block. So when you try to figure out whether someone is at home or not, just be patient enough and wait for a few packets and see whether they are still always the same. I mean, they're encrypted, you don't get any clue what's in there, but if they are the same, then you can basically conclude that there is no one at home because they're not using any energy. But they were pretty clever. They mandated to prefix the value with the date and time record. And if you flip through the standard, you will come across the date and time record. Unfortunately, the date and time record is just minutes. And if your meter is going to send you information every 10 seconds, you're lost. So it doesn't help. There are more actually, but you must figure it yourself. Then I thought, okay, let's give mode 5 a try. What they're doing there is they still use AES in CBC mode, but they're not using a non-zero IV. So to analyze it, we basically must have a look at the IV construction now. They take the IV from the manufacturer. This is a good idea. Now it's probably not changing over the lifetime over the meter. It's not any better. So there's the address of the meter. As this is the serial number of the meter, usually it doesn't change either. The only thing that changes is the access number. So every packet should have another access number. Actually, it should be incremented. So let's see what happens. I mean, it's 255 values. So if your meter sends your information every 10 seconds, the access number will roll over after about the 45 minutes, and we have the same packets again. So just be enough patient and wait the 45 minutes, and you should be easily able to determine whether someone is at home or not. Then I thought, okay, last but not least, we still have this encryption mode 1 at the link layer. It's counter mode. The issue with counter mode is if at some point the initialization vector repeats, you could get some plain text out of it. So what you do basically is you calculate or you encrypt the IV and XOR it with the plain text. And if you use the same IV, you could basically do this mathematic, and this is an example of it. So we do have a plain text of an actual packet of 341 kilowatt hours and a 341 and 12 kilowatt hours. And the difference of these two plain texts is 1C. And if they have been initialized the same way with the same IV streams, then you basically can capture two ciphertexts, and if you XOR them together, you get also a difference of 1C. Now what we are going to do with this 1C is we figure how much the difference could actually be. So we'll try to find the nearest pair and the most wide away pair. So, and this tells us basically the consumption must have changed between 4 watt hours and 28 watt hours. Is this an issue? I mean, if you buy shares from a company, it would be good to know whether they have some win or loss, or whether they are better on the way or not. So you mustn't necessarily know how much energy they used. It's sufficient if you just recognize they used more energy or less energy, because this basically tells you they are more efficient or less efficient, hopefully. Okay, but to basically answer the question whether we could use it as an attack or not, we need to answer the question whether we could make the IV to repeat or not. And for that purpose, we need to have a look at the IV again. It's built from some static components, so the manufacturer ID doesn't change, the address doesn't change, then there's a signal communication, doesn't change much. And there is a field which signals the session counter, and it has a time field. So this one is going to change. This one is pretty predictable, and this one is also pretty predictable. So it's difficult. It seems as IVs don't repeat. So it would mean I couldn't actually run the attack I had in mind. By the way, if you can predict the IV in counter mode, your security of the AES 128-bit is reduced to 85 bits. Still enough today, maybe not tomorrow. However, so if we can get the time to repeat somehow, we can get the IV to repeat. That's the bottom line here. And if we want to get the time to repeat in the meter, we must somehow figure whether we could adjust the time of the meter. And for that purpose, I was digging into the special protocols. So there are special protocols for alarms, errors, application resets, and there are clock updates. And actually, set, add, and subtract from the clock counter doesn't need any encryption or authentication. So we could actually update the clock of such meter, provided it is implemented. We have keystream repetition, means we could get the information from the ciphertext. Okay, how about integrity? So what does happen if I can manipulate packets and throw them to the meter or to the collector? In general, there are just two mentions on how to implement authentication. There is some integrity protection using these CRCs at the frame level, and they propose to use signatures for consumption values, but actually it's a sentence or two a mention in the standard. There are no MACs yet. So basically means there's no integrity protection, so let's try to figure what we could do because integrity protection is absent. What we could try is we could alter IVs, because if we could alter an IV, then we could basically manipulate the plain text. So it doesn't make much sense to do any bit flipping on the ciphertext in CBC, because if you decrypt it, you just get garbage. But afterwards, the IV is applied to the plain text there. And so if you flip a bit on the IV, then it's directly flipped in the plain text. So can we do it? The IV is built from that part. So if we manipulate that part, then actually the counterpart who's receiving the packet can't find the correct key. So no good idea to manipulate over there. Version and type could be part of it, but I wouldn't use the version to actually look up the key, because if the version of the meter changes, bad idea. And we could actually try to manipulate the access counter, which basically is an indicator for the number of the message. If we do that, we just destroy the trailing 2F, which are used as a padding for the packet. But as the wireless meter protocol is built with fixed length value, basically, where you always tell the receiver how many bytes of values are being appended, so they don't really need to have a look at the trailing 2F. So I don't think any developer is going to have a look for it, whether these are valid 2Fs or not. So there you could be able to manipulate, actually. And if devices share the same key, so if you flip the device address and the 1,000 devices there have narrow device addresses, you could use it actually for bit flipping, because if they have all the same address, the receiver would still find the correct key. So I made an example. if we have an original value, and we read it actually from the meter display through 341 kilowatt hours. And if we'd say, okay, this is too much for my bill, I'd rather prefer to pay less. We can read the standard IV from the packet because this is not encrypted. And then we figure how much we're going to pay. And keep that in mind because we'll need to manipulate the IV over there. And this will basically turn then the plain text into the manipulated plain text. So we have the ciphertext block. This is the original ciphertext being sent to the collector. The static key will be applied, and here we flip the bit. And this will basically also cause to flip the bit in the plain text. So we basically flip bits here, and this will turn the numbers, and we'll finally have 144 kilowatt hours. So we've basically cut our electricity bill into half. You could do it the other way around as well. So you could basically do it in direction of the meter. So if you want to send, for example, a command to the meter, you could use this technique as well. There's another issue. You could basically tell the receiver how many blocks are being appended which are encrypted. And then they go and take this part, decrypt it, but you could still append more unencrypted information. And some of you might have heard of HTTP parameter pollution. What I describe here is basically the same for the protocol. So what we do is we have a standard encrypted packet. So it says the length of the packet is 1E, and the bold text is the 16 bytes, a single block AES encrypted message. What we do is we attach a plain text, a standard value. We actually have to adjust the first byte because it's indicating the whole length of the frame. We don't touch the encrypted part at all, and we just append the plain text. So now it basically depends on what the developer did within the meter or within the collector. So if they take the first value, which is encrypted, or whether they use the second value, which is plain text in their algorithm. So I took basically the plain text and appended it to the encrypted part. Then I had a look at the extended link layer integrity protection. So they were pretty clever. They used CRC, and they did encrypt it actually, in hope no one would be able to manipulate commands. What you see here is a command to switch a meter on or off, the official command. So, and it basically yields a CRC of CC22. There's a little neat tool, it's called Revenge, which you could use to calculate the CRCs for various polynomials. And what I did is I basically calculated the CRC over this switch on command, and I also calculated the CRC over the switch off command, which is F147. And then there's again a little mathematics. So you basically want to send the off command, or at least you want to let the meter think it's an off command. What we intercepted is the first part, so the intercepted ciphertext, the first line. We know how the on command looks like. And what we do now is we have calculated the CRCs over these two commands. And we do now some magic. We take the ciphertext, XOR it with the original plain text, and XOR it with actually what we would like to have. And we send that ciphertext to the meter, and it's going to switch off. There was never a need to know the key. Not at all. And all because there is no integrity protection. So this tells us even an encrypted CRC is just no use. And there is no integrity protection at other parts of the protocol as well. So, time for demo. It's kind of difficult to bring meters and stuff when you arrive by plane. So I brought some little sniffer devices. I have 2 of them plugged into my computer. There is a collector device, which is actually a piece of software running on my computer, but behaving like a real-world collector. And there is, instead of the meter, there's a little simulator device. This is over here, so if I switch it on, so it's on now, and it steadily increments, or it sends an incremented number. It simulates a water counter. But what I do now is basically use this infrastructure to show you some attacks. So the meter is going to send its information to the collector, which is a piece of software on my computer, and I'm going to send it to the sender device, so to repeat information or to manipulate it or whatever. You could use those sticks. There's also a little transmitter device. It's called the CC1101 from TI, which you could use, but you could also use general purpose radio equipment. There is a GNU radio project, actually. You mustn't take photographs. It's all on our blog afterwards. So. And if not, just ask me. There's a GNU radio template for wireless ambus as well. Okay. So I do have a virtual machine. We do have a piece of nifty sniffer software again. It's all written in Google Go. I start my device now, so you see it. It should steadily send information. Oh, come on. Yeah, here we are. There's no such device. This is not very nice. Better. Yeah, he's probably right. I'm sorry. It's a bit difficult. So if I plug them the wrong way, then you're going to go for coffee. So it's all disconnected. Here we go. One is here. The other one as well. Here we go. So it's sending new messages. Here it is. Should be more or less right time. There's a new popped in. You will see some basic information, so how long the frame is, the control byte, what manufacturer it is, so this is Amber Wireless. Then the ID, and it's going to tell me, hey, I'm a radio converter. Actually, it's a simulator. Usually you see here whether it's a water meter, gas meter, heat meter, whatever it is. That's the access number I told you. It should be incremented. Yes. And here's the IV computed. And there's another device over here. So this is the emulation of the collector, so the one who is collecting all the information. You see here, the meter sent us a value of 684 over here. And here's the key for the device. And if we just run it again, so it's counting up. All right, so we are with 687. What I do now is I just go to the sniffer. I take one of the old packets. So I just replay it. Go to that one, and basically we sent an old value to the collector again. It's just I just repeated the message again, and he's gonna pick it and takes it for granted. That's it. I have another neat demo. So I told you there is this plain text appending issue, and actually the device we simulate over here behaves the wrong way in real world as well. But I can show you how you could achieve this attack with this little tool. So what we are going to take is one of the messages, and you see here it's going to send an information. It's called Amber Wireless Test Module. We'll put something fancy here. For that we need to do some magic again. So choose the value you like. For example, I like Hack in Paris. So we need to reverse it, and we need to have the hex numbers of it. Here we go. So you see here is the hex representation of that string, and the first 3 bytes are actually indicating, hey, this is a string. So I'm going to pick that, and I take an old message. I'm going to pick that, hey, I'm a string. I'm going to pick the bytes. Here we go. Put them over here. Need to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Should be OC, right? No, B. B, C. It doesn't really matter. And what the tool actually does, it just adjusts the frame length automatically. I'm going to send that. So, ta-da, Hack in Paris. So, but you maybe recognized I just stopped the meter, because in real world it's slightly more difficult. Because when I just send another value, the meter will still send its original value a few seconds after. So what you need to do is basically capture a packet, then somewhat either shield the meter or take a big hammer and break it, and then repeat it. But it's kind of difficult because utilities do employ some sort of fraud detection. So if your energy bill just drops, then yeah, you're lost. So what you need to do is capture all the packets in time and just delay them and send them. That's far better. Or you could also figure what the actual delay is between the packets and jam the packet and send your own packets in between. But make sure you don't use more energy that you are actually gaining. Okay. Yeah, so what would you do then? Go and war drive, so drop your devices, capture packets, or drive around. Install a big sender, makes a good picture for this con, and then you're gonna send or repeat the disconnect messages. Yes, make sure you bring flashlight, it's gonna be dark. I tried to sum it up and I stumbled over that company. They basically specialize in wireless ambush installations, wired and wireless, and their company name brings it pretty much to the point. So we have low key sizes, zero consumption detection, disclosure of consumption values. We could easily see errors and alarms. There's information disclosure, man in the middle, key disclosure. You could manipulate consumption, and you could also organize for a blackout. But people have figured it as well. They have published a new standard in January this year. They have 2 new modes, 7 and 13. 7 does some requires some integrity layer, which does some CBC MEC, I guess, and does rotate keys. It calculates keys dynamically, so it should be pretty fine. And they also figured, hey, we could use TLS. 1.2 support for wireless ambush. So if you buy any meter, then please go for these 2 types of protocols. That's it. My battery pack is empty.